Cool. So, looking at the Dithered Raymarching project here, kind of what that's doing. So here I've got no dither pattern applied. I'm just quantizing to, in this case, 2 bits, which may actually be 3 bits because when you bring it down to 0, it's 1 bit. Anyway, so as you vary through the bit depth, you go back to the full bit depth image here. So yeah, as you bring it back down, you're quantizing to fewer and fewer bits, and you start to see these quantization artifacts. So to counter that, we've got a process called dithering, right? So the color spaces are not quite implemented yet, and I'll get into what that's the reason for that later. But so now what I have implemented is the dithering patterns. So what they're looking at here is now when I do that quantization, I have some small offset that I can apply on a per pixel basis, which helps counter the effects of the banding that you see with the quantization. So basically what's happening here is here, this one's a Bayer matrix. Then I have like a blue noise texture that's single channel and it's static. And I have one that's got an RGB blue noise texture, so each channel has its own independent value. And there's cycled mono blue, which basically is what that's saying is it uses this interesting little trick based on the golden ratio to cycle the values that are held in the blue noise texture over time. So it's looking at what frame we're in, and it computes that dither offset from that. So same thing with RGB. Then there's uniform noise, which is and when I move the camera, you can kind of see where that's static. That might be something to introduce some kind of time varying behavior to. And I'm hoping that this at least partially comes through on the video, because bandwidth issues, it's really not, is it? I just have the stream up here. Try and set the bandwidth right. Wow, that's really ruining it, isn't it? No, it kind of comes through. Okay. There's something there. Okay, anyway, so then, all right, so you've got the uniform, and then you've got what's called interleaved gradient noise. So this is another noise algorithm that runs on the GPU to generate this kind of a staticky little thing here. This other one comes from a fellow with the last name Vlachos, I think that's how it's pronounced. This is a variant of that. And some of these look really good, but so I haven't exactly computed the combinatorics here, but yeah, so we'll just run through the rest of these. But so basically, looking at this, it's going to be there's all these different color spaces, right? There's all these different noise algorithms, and then there's 2 methodologies to do the dithering. One uses the method from the previous project, which does an operation that I've been calling bit crushing, which comes from audio, like digital signal processing type stuff. Basically, zeroes out the low bits of the value, the color value in this case. In audio applications, you're looking at basically in essence it's reducing the precision by taking those low bits and blowing away the data there so that only the high bits remain. So basically, like I say, that's not fully implemented yet, and I can look through these again with the different things here. So just quantized Bayer matrix, the static blue noise, cycle blue noise, which looks a little chaotic in the 1 bit. Uniform noise, interleaved gradients, and then the other types as well. Huh. That one looks really good for the low bit depth. Huh. Yeah, but anyway, these have distinct characters to them. There's a certain quality to each of them. One that is the Bayer matrix is a very classic pattern. It's got a very characteristic kind of pattern that it applies to all the shapes here, or the color gradients, I guess. But yeah, some of these other ones are interesting too. But so basically what the idea here is with the with operating in different color spaces, the bit crush and exponential reduction of precision is just that, right? It's a reduction of precision. So the use of these different color spaces comes in when basically, okay, core concept is like, okay, here what I've been showing off so far is all in the RGB color space. So I start with an RGB value as a result from this Raymarching process. Okay, so that's getting me geometry, that's getting me shadows, that's giving me ambient occlusion, that's giving me all this stuff as image data coming in. Well, then the idea with the color spaces is then, okay, I have that RGB data coming in. All right, now I'm going to take that and convert to yeah, okay. I'm gonna convert to then this. Can't tell if audio is coming through. It is, okay. Anyway, so basically the methodology here is convert to this other color space, reduce the precision, and then convert back. So here I'll show kind of what we're dealing with here. This is the previous iteration of this project. This exclusively used the Bayer dithering matrix. But we can see no dithering. This is the direct result from the image. This is dithered in the HSL color space, the HSV color space, the RGB color space, the YUV color space, sRGB color space, the XYY color space. I really like this one, the way it brings out the chroma. It's a really interesting way. HCY, it's got some artifacts. YCBCR, so it's defined in a different area, different range, so negative 0.5 to 0.5 rather than 0 to 1. So that's where these types of color skew type stuff is happening. But anyway, so these different things, they've got different properties to them. So basically what this project is doing is looking at, you know, what's a cool way to combine these, and probably eventually, yeah, it'll be a figuring out a combination of these that produces a really good look. Because right now, like I say, this is all occurring in the RGB color space. I don't have it implemented quite yet. I have a lot of the code implemented as far as conversion functions, but the infrastructure code is not quite finished yet. So yeah, so right now it's mostly just dither patterns that exist as a selectable thing, but yeah, these are right. And if you look at the combinatorics here, I think I have 10, 12 of these color spaces, and then I've got I think 10 of these, and then 2 of those. So you're looking at like 200 combinations roughly, and then you've got all the different bit depths as well. So really, I'd only consider it valid up to about 4 bits, because then you're not seeing much effect from the quantization past that. You see like a little bit, but it's not huge past like 4 bits. So yeah, it's a neat little project. Having some fun with it.